So we're going to be talking about min heap in this video, and min heap is one of the binary heaps that can be used as a priority queue. Now, previously we talked about a binary heap and has these two properties, shape property and the heap order property. Okay, we haven't quite talked about the heap order property. So the heap property says kind of the key in each of the node must be either greater than or less than the key in the node's children. So usually when we talk about priorities, we say, the data with the smaller priority is the one with the higher priority, because we often say, our number one priority, right, is to do so and so. So we'll study what's called a min heap, and that min heap is one of the binary heaps that has the property, again, the shape property, which that it's a complete binary tree, and the heap order property then is the key stored in each of the nodes is less than the keys in the node's children. And obviously when you see the word min heap, there's also the max heap, but again, we only worry about min heap from now on. So looking at these heaps here, pause the video and try to figure out if these are min heaps based on the previous definition. Assuming you have done that, let's look at these together. So the first heap, the first tree, is not a min heap because of the node with the data 8. The number 8 is greater than its left child. So for a min heap, it must be smaller than. So this is not a min heap. What about the second one? Well, the second one, it doesn't satisfy the shape property, because at the last level, one of its node is not as far left as possible, right? There's a little hole here. Okay, and this last tree, though, it is a min heap because, well, first of all, it satisfied the shape property. Every level is filled except the last one, and the last level, everything is as far left as possible. And then it also satisfied the heap property. You can check every single node, and every single node is smaller than both, all of its children. Now, one thing I want to point out is, even though this kind of looks like a binary search tree, it's not a binary search tree, okay? And the reason for that, obviously, is in this place, that, a binary search tree would require the left child to be smaller than the node and the right child to be bigger. And this is not. So min heap might look like a binary search tree, but it's not. So how does the min heap address the concern we have previously with using ordered linked list or binary search tree as it's a priority queue? Well, the really cool thing about being in a complete binary search tree is that it allows for two things. One is min heap is always balanced, right? A complete binary tree is balanced. So we know that in a balanced binary tree, most of the operation will be out of log of n. Okay, and then the second good thing is that the fact that every level is filled except the last level, and the fact that the last level is filled all the way to the left, is that it allows that instead of being stored like a binary search tree with a lots of overhead in forms of the child references, as we discussed earlier, a min heap can be stored in just an array with no overhead. Now, there is no array in Python, so we'll use list. But the same idea applies, that there is very, very little overhead. And we'll see how that works. So like we said, instead of storing the heap like a binary search tree in this form, we'll just store it in an array. And the way that it's done is we'll put 1 here, the first level, 1 here, and then followed by the second level, 3 and 6, and then the third level, 17, 19, 36, and 7, and then the last level, so on and so forth. Okay? And well, a couple of things to note in the array representation of the min heap is that, well, we skip the element at index 0. We actually don't store anything there. We'll see why in a moment. And the second thing is, let's say the children of node 3 is 17 and 19 at a particular position that makes them very easy to find. And what I mean by that is, let's look at an example. So let's say we're looking at the element at index 2, right? Its left child is at index 4, its right child is at index 5. Right? So kind of remember those numbers. Now, the element at index 3, okay, its left child is at index 6, and the right child is at index 7. Okay, I hope that you might start to see some patterns here. So I'm going to ask you to try to figure this out yourself. Try, for example, look at the element at index 7. Try to figure out where its left child is and where its right child is by looking back at this picture here. Okay, so assuming you've looked it up, and basically the left child of the element at index 7 is at index 14, and the right child is at index 15. And I definitely hope by now you see the pattern here. And that is basically the for each element at, let's say, at any index, its left child is at the index that is 2 times that index, and the right child is that number plus 1, right? Which is what it says here. And this kind of a simple math here is kind of enabled by the fact that we put the first element in the index 1 instead of index 0 like we normally do. Okay, so anyway, let's formalize this. For an element at index k, its left child would be at index at k multiplied by 2, and then the right child would be at k multiplied by 2 plus 1. Right? And then the last fact, even though we didn't explicitly state this, but it should be very obvious to see that for an element at k, its parent is at k divided by 2. It's an integer division. Okay, so it doesn't matter whether it's a left child or right child, its parent is a k integer divided by 2. Okay, and if make sure that you look at the pictures, look at the previous pictures, and prove to yourself that that is indeed the case. Now, obviously, there are special cases. For example, the root would have no parent, and some of the elements would have, either no child or just one child. But this is what gives min heap its space efficiency, because using some very simple math, we can figure out exactly where the parent and where the left and right child of a node or of an element is, without using explicit pointers or references.